I guess we'll need to kill it off this one. Yep, sounds good.
Good evening, everyone. Welcome to the Tucson Amateur Astronomy Association September meeting. We meet the first Friday of every month at 6:30, and we're so glad to have everyone here who's with us tonight. We have people in the room with us in person. We have people on social media, and we also have members who are attending via Zoom. So we are delighted to have all of you, and if any of you, have any comments that you need to make at any time, if you are in the room, you can get our attention by raising your hand. If you are on social media or on Zoom, then you can type into the chat, and we will be taking questions for our speaker through the chat. Whenever you have a question for him, you can put those into the chat. We will maybe hold some of those until the end so that we don't interrupt his presentation. But if there is something that you don't understand about a slide or something that was just said, please let us know in your message that this is, a momentary thing so that we could handle it quicker for you. My name is May Smith. I'm president of Tucson Amateur Astronomy Association, and we have people helping us with our social media tonight. We have Jim Knoll, who is working diligently on the computer right now. And we have Susan Knoll, who's going to be operating our camera, and Terry Lappin, who will also be helping on social media. And Jim and Susan will be operating any questions that you have through social media, so they will make sure that those get conveyed to the room here. For people in the room, when you have questions, you'll need to pause a bit whenever you raise your hand and we're ready to recognize you, because I'll have to take the microphone to you. You will need to speak through the microphone so that everyone can hear you when you're in the room. So we'd like to get started tonight. We've got several things on our agenda for our meeting tonight. Our first presentation is Dr. Christopher Wilmer, and some of you will have seen information about him that we sent out through social media and that we sent out to all of our members, describing his real extensive background in astronomy. And he is an associate research professor at the University of Arizona. And he's going to be sharing some special things about the James Webb Telescope project. And we're very happy to have you with us tonight, Christopher.
Okay, well, thank you. So I'll be talking to you about the James Webb Space Telescope and what we have been doing, and the observations that cover from solar system objects out to the earliest universe. So for those who are not astronomers, which is not necessarily this public, but for those online, there's some basic concepts in astronomy that it's good that you understand. And some of it's to do with jargon. For instance, in astrophysics, any element which is heavier than helium is called a metal. Thus, oxygen, carbon, nitrogen, neon, these are all metals for an astronomer. Another concept, which will come later on, is a weak lens. This is a lens that you introduce in the focal plane to add in some defocus on your source rather than defocusing your telescope, which is using the observation of bright sources and telescope focusing. The type of observations that we do can be either imaging, which is like taking pictures with a monochromatic camera, and spectroscopy, where you decompose light through a disperser. Even though for the public in general, this is not a really exciting thing, for astronomers it is really exciting because we really understand many of the physical properties of the sources that we're observing. Two additional modes of observation which are used by JWST are what are called the time series observations, also known as CSO, and high contrast imaging, which is using coronagraphs or interferometers, but we'll come see those later. So decomposing the light basically is you have a source, you put its light through a disperser, which we can see here in Tucson with the rain, and then you get this spread of colors where you actually bending the light in different wavelengths to different positions. And the colors that you measure, they're related to some of the properties of your sources. So on the left, we have a one-dimensional spectrum of different types of stars. And on the right, we have the two-dimensional spectrum, but we also have the colors. So if you take a band on each of these regions on the right side, you'll get a different color. And the ratio between those will tell you a lot about the internal properties of your object. And this is why you use filters in detectors in astronomy. And here I have an assortment of photographic filters, but they kind of match what you see on the right, which is the spectrum of the sun, and it gives you roughly the ranges where each of those colors are valid. So when you use basic colors, you can actually quantify some properties of stars. So in the early days of astrophysics, people found out that by using the brightness in a given plate, and if you use plates of different colors, because this is when it was started, you could actually build a diagram which told you a lot about the physics of these stars. So as you go to brighter and bluer stars, you're looking at higher mass objects, whereas if you go to redder colors and lower luminosities, you're looking at low mass galaxies. And this has a lot of implication on how fast these stars evolved and how many of these stars you're going to find within a population of galaxies. When we talk about galaxy spectra, it is not as simple because these are composites. So you have different types of stars which contribute different numbers of amount of light. And what you'll see is you'll see an integrated spectral energy distribution. So on the right, we have what is typical of a quiescent galaxies, like elliptical galaxies, which is dominated by older populations, and they tend to be luminous stars. Whereas on the right, we have the typical spectrum of a galaxy which has a lot of young stars, which emit a lot in the blue, and they also have emission lines, which are caused by the light of these stars exciting some of the gas that's in the interstellar medium of these galaxies. When we look at a galaxy in different wavelength or frequency regimes, we can see completely different. It's a completely different appearance. So this is M31 in Andromeda. On the right, we see the X-ray image, which is mainly dominated by X-ray binaries in the galaxy. As you go to the ultraviolet, you actually see the young stellar population dominating, and this is found in the arms of the galaxy, though you do see some contribution in the core. When you go to the visible, you actually see a large mix of populations, but you also see a lot of absorption by dust. When you go to the infrared, you see all this dust emitting light. And if you go to the radio, and this could be 21 centimeters, then what you're seeing is a neutral hydrogen emitting light. So depending on what wavelength regime you're looking at, you're going to see a very different image of your galaxy. When we come to time series observations, basically you're staring at a star, in this case is the sun, and you're watching something go over it. In this case, this is the transit of Venus of 2012. And you see a light curve of this event where your planet goes over the star and it comes out. Though the scale is not very clear, this change in luminosity is only of the order of 8%. When you're looking at exoplanets, this will be a much smaller difference, but the technique is the same. And of course, when we talk about high contrast imaging with a coronagraph, this is a typical example. You have the star, which is a minus 26 magnitude object, and you can actually attenuate its sun. That allows you to see an object which is much fainter. In this case, it's Regulus during the 2017 eclipse. And this technique is used in astronomy quite often. So talking about the James Webb, the first conceptual designs for James Webb began already in the late 80s, even prior to the launch of HST. And this is part of the NASA's Cosmic Origins program, which has a concern of connecting life on Earth with the physics that created life on Earth. So basically the questions are, how did the first stars and galaxies form? What is the stellar life cycles? And how do the elements that you find in stars and the Earth evolve? How did galaxies and supermassive black holes evolve? What is the evolutionary history of the Milky Way and its neighbors? And how do planetary systems form and evolve? So basically, this program tries to explain the evolutionary connection between the primordial fluctuations that we detect in the cosmic microwave background and the conditions that enable habitability and possibly life on planets. James Webb Telescope is actually like a time machine, particularly when you're probing the redshift frontier, because light has a finite travel time. And as we're measuring objects at greater distance from us, we're also looking much further into the past. From the cosmic microwave background is the most distant feature that we can observe from Earth. And at the time that the cosmic microwave background was emitted, only the primordial elements like hydrogen, deuterium, helium, and lithium existed. Through the combination of theoretical models with observations, it is possible to infer how the other non-primordial elements were formed. And one of the aims of Origins is to measure when these non-primordial elements were formed and how this fits into our models of star and galaxy evolution. For instance, this is an interesting take on the periodic table, where we also show not only the elements, but we also show what were the types of processes that created these elements. So we can see the Big Bang fusion, which has mainly hydrogen, helium, and a bit of lithium. Then we have cosmic ray fission, which is mainly for beryllium and boron. And we have elements which come out of massive stars, dying low stars, merging neutron stars, exploding white dwarfs. So this gives us a very good connection on how these elements were formed and the history of the universe. If we have a timeline of the universe, we know that the initial singularity, the Big Bang, created a universe that was completely ionized. And while this universe expanded, it also cooled until about 400,000 years after the Big Bang, which is the top axis. The temperature was low enough that electrons and protons could actually form atoms of hydrogen. This is called recombination. After that, we have a span of about 500 million years, or 100 million years or more, which are called the Dark Ages, because there was, even though you had structure formation, it was not time enough that you could have the first stars being formed or the first galaxies. Once you start having star formation, these stars start emitting radiation, and they will start carving holes in this distribution of neutral hydrogen. And as more and more stars they start forming, you actually get more and more larger bubbles until at about 1 billion years after the Big Bang, the universe became completely transparent because all the hydrogen atoms got ionized. And this is something that we measure using spectroscopy in real life. To study these themes, we have to go into the infrared for many reasons. First, if you know what a black body curve is, we will see that planets are colder than stars. And as you go into the infrared, that's where there's the greatest contrast between their hosts, which means that is where the ratio of light coming from your planet and that of the star is largest. We also go into the infrared because we have less dust absorption than in visible wavelengths. And depending on the wavelengths that you go to, this dust will actually be emitting. And this is certainly possible in the wavelengths that are accessible to James Webb. For instance, this is the Carina Nebula, which was shown on the July 12th, where we see in red a lot of emission, which is coming from the dust in this region of star formation. We also, as we go looking at progressively more distant galaxies, their light gets shifted into the infrared because of the expansion of the universe and the Doppler effect. So here on the left, we have a standard spectrum in blue of a galaxy at rest. And we see a feature at 4,000 angstroms, which is due to absorption by hydrogen. And or in this case, it also has the calcium lines. As you go towards the green spectrum, we're going to redshift of a half. We see that it has shifted position. As you go to 1, it shifts even more. Now, when we go to the plot on the right, we see that this break even moves out of what is the visible, because on the left we have visible wavelengths, on the right we have mostly infrared. And when you're talking about redshift 10 galaxies, which is roughly the redshift frontier, you're very far in the infrared. So you cannot do this from the ground, even at that kind of wavelength. This is a demo of a method of measuring redshift, which is called photometric redshift. And this is a rebel of a slide because it does not allow me to repeat. So I have to go back 1 and go forward 1 so you see the concept. If you look at the points up top, they go shifting as your spectrum moves towards the right. In other words, as it goes towards higher redshifts. And this is a technique that we use to measure distances of many galaxies at the time when they're too faint to get actually spectroscopic observations. So one of the other issues that we have is that infrared observations from ground-based observatories are very impacted by the emission by the atmosphere and also by the telescopes themselves. And there are also regions in the atmosphere where it is opaque to light and no light from the sources can be detected. And therefore we have gaps in coverage. So for these reasons, to properly address the origin science themes, the observations need to be carried out from space. While Hubble Space Telescope is in space, its instruments are not cooled to the level where the infrared detector's noise becomes negligible. So this graph actually shows where different types of observatories are most effective. So we have invisible light, the ground-based work well, and some of the radio arrays also do well. But in the cases of ALMA, for instance, which is a big telescope array in Chile, or the SKA, which is a large array in Western Australia, a lot of these need very dry atmospheres. Some observations you can do with SOFIA, which is an airborne observatory. It goes over 99%. But for a lot of the other science, you have to go into space. And these are all the satellites that we see here. Is all of this clear to people? People have anything to ask? Otherwise, we'll continue. So, some trivia. James Webb obviously is an infrared optimized telescope, which was initially designed to study the high redshift universe and search for cold companions of stars. And to me, it was pretty amazing to see this was already something that people were aware of in the late 80s. It is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. It is a telescope that's placed in a solar orbit around the second Lagrangian point because it allows an efficient passive cooling as the telescope is always pointed away from the sun. It keeps James Webb out of the shadows of Earth and Moon, so the solar panel is always illuminated. It is easily to communicate with because it's always visible from some deep space network station. It minimizes the use of propellant because you're in a semi-stable position in the sky. And it has none of the limitations that affect HST by being in the Earth's orbit, which is a pretty, there's a lot of change in the environment because you're either in the sun or you're in the shade and things like that. So this shows what is the orbit of James Webb around L2. It is about 1 million miles from Earth, and its epicycle around the Lagrangian point is actually larger than the orbit of the moon around the Earth. And it takes about 6 months to do a full orbit. But this trajectory is excellent for getting rid of, let's say, accumulated angular momentum, and it is very efficient to conserve energy. In other words, propellant, which gives it a longer life. So the components for James Webb are basically what we call the optical telescope elements, which is the set of mirrors, which are all gold-plated to optimize the infrared reflectance. You have the integrated science module where all the instruments are posted, and all of these are on the far side of the sun shield. And then we have the spacecraft bus, which is on the illuminated side of the telescope. And that contains the sun shield, navigational devices, antennas, solar array. The primary mirror of James Webb is about 6.5 meters, and it's made out of 18 segments of beryllium because this element has very small weight and low expansion coefficient. And this is comparable to the size of the mirror of the MMT here in Arizona or the Magellan Telescopes, which the U of A operates in Chile, together with other institutions. So these are pictures of the mirror in several stages of James Webb's life. In the left, we see it before it went into the big cryo chamber that was used for the Apollo missions to make tests, which was the first integrated test of instruments and the mirrors. In the middle panel, we have it as the first test using the solar shield were put on it. And on the right is when it was being packaged to be sent to French Guiana before launch. James Webb Space Telescope has 5 instruments. One is the fine guidance sensors, which are used to track your guide stars while you're acquiring data. You had the mid-infrared instrument, which measures photons coming from about 5 microns to 28 microns. You have the near infrared camera, which is one of the main instruments. It's an array of 10 detectors, which is used also for the wavefront sensing, which is basically focusing the telescope. You have the near-infrared imager and slitless spectrograph, which is also an imager, but it allows taking spectra of different types. And you have the spectrograph, the near-infrared spectrograph, which is one of the most exciting instruments in this, but it also is one of the most complicated. All these instruments are passively cooled to about 37 K, thanks to the sun shield, with exception of MIRI, which requires an operating temperature of about 6 Kelvin, which is obtained by using liquid helium. And basically, this shows which are the instruments and their wavelength ranges and the PIs who actually directed the construction of them. And this is what they look like on the focal plane. So we see NIRcam, which is roughly to the center, and this is used for the telescope focusing. You have the fine guidance sensors to the lower left, and you have MIRI in the upper right, NIRIS and NIRSPEC, and these are their locations there. And it also shows the different types of spectrographs that are available on NIRSPEC. This plot shows you the wavelength domain and the observation modes. So you have coronagraphy, which is high resolution imaging, and all instruments excepting NIRSPEC have that. And all of these instruments have ability to take spectra of sources. The types of objects that James Webb is planned to observe is definitely not a complete list. I would say it's almost everything but the last item. So it cannot observe any object to the interior of the orbit. So it cannot observe the sun, the moon, Venus, and Mercury. The rest is all fair game. And this just shows some assortment of the objects that have been observed with James Webb so far, which range from nearby galaxies, distant galaxies, the Carina Nebula, a planetary nebula, brown dwarf, and even Jupiter, which is the brightest object I think it will ever observe in its life. Is all of this clear? Otherwise, we go to commissioning tasks. The commissioning allows you to characterize and make initial calibrations of an observatory, and this is true both for space and for ground-based. These calibrations involve the mirror alignment, the precise map of instrument distortions internal. So you look at your image and you try to find out how you convert your positions on your instrument to the coordinates in the sky. You have to have a precise map of the focal plane in orbit so you can know what offsets you have to do when you're doing a guiding or you're going to a new object. You also have to take some dark and flat field images, which I think for most of this public is something well known because you do this a lot in astrophotography, and also have the throughput measurement, or basically the flux calibration. During commissioning, we had to test at least 17 observing modes. These are not all, but these are the majority of the observing modes that will be used during the operating life. A few additional observing modes will be tested during cycles 1 and 2. To do these tests, what we do is we carry out imaging, which can be either wide field or high contrast. We take spectra, we take time series observations, and we also tried guiding on moving targets. So some of the main results that we get from commissioning is one of the big concerns that we had, whether there would be any type of contamination by water ice that would be residual once the rocket was launched. We find no evidence of water ice on the optical path that makes any difference to the observations. We do find that the throughput of the mirror and instruments is higher than requirements, in part because we don't have this contaminant present. We certainly we actually are a bit better than requirements when it comes for the resolution of the telescope, where originally the requirement was to have a diffraction limit at about 2 microns. We actually have it by diffraction limited at about 1. We do find that the telescope pointing is very good and very stable, so you can track an object within 1 milliarc second. And James Webb Space Telescope is able to track moving sources without any effect on the image quality, and all of this is good news. So this shows a difference between the model that was expected for the water ice, and in blue and orange we actually see the actual observation. So we don't have attenuation in this pretty large range of wavelengths, and this is true not only for this GRISM spectrum, but it is also true for all the other instruments. This shows what the requirements were. So these are the inverted triangles on top, and the histograms show what are the measured resolutions that you can get from using James Webb. Now we see that there's 2 different colors here. The lighter color is after we had an event which struck one of the mirror panels, and this did decrease slightly the resolution, but we're still much better than the requirements were. And this is true for all the instruments on the telescope. Many of you may recall the bright star. This is the first image that was made public once the telescope was in focus, but this is the actual full field of it. And what is striking is not only the quality of the star, but the amount of galaxies that we see here. And even someone whom I know, just for fun, used a very contrived way of classifying these galaxies from a JPEG image, which was kind of funny. This shows the focal plane now, how it is completely mapped using what we call the Large Magellanic Astrometric Field. This is a field in the Large Magellanic Cloud which has been observed for many years, for which we know very well the proper motions of sources. And it was planned already thinking on the calibration of the James Webb Space Telescope. And the interesting thing here for me is that you can see MIRI detecting some of the dust that's emitting in the LMC, and you can actually see direct images of stars through the microshutter array that is used on NIRspec. An interesting test is this one of moving objects. It's maybe kind of hard to see it on this big screen, but what you do is you're tracking on the source itself, or you're following your source with the same speed that it's transversing on the sky. And you should, if you did a proper stack, this source would be always in the same position. But to demonstrate this, we created a stack where we're centering each star, and we just see the movement of the nearby asteroid that is shown in different colors, in blue, green, and red. And this is one of the big tests that was done, and this allows for fairly rapid moving asteroids or comets to be followed with this telescope. Also, another moving target that was observed was Jupiter. And this is a picture that came out during commissioning, not the one that came out on NASA a few days back. And one of the things that got a lot of the astronomers surprised is this presence of haze, which we don't know what it is, but it was clearly seen and no one could explain it. And of course, we have some of the satellites of Jupiter, and we have also the aurora, which looked really nice on the later images that were made public in late August. This here is an example of the use of a weak lens and the GRISM for time series observation. So if you recall, we saw how the transit of Venus was. You can do this also measuring a star. And one of the ways that you can beat saturation is if you disperse the light with a weak lens. So you're still measuring all the light of your star, but you're not saturating the pixels, which in the case of this type of detector is really important. Otherwise, you start getting nonlinear effects, which could mask what you're trying to measure. Or you can disperse it in the GRISM, and then you have several wavelengths and several pixels that you can use to estimate what your transit curve looks like. So this was a pretty successful detection. I think this is an exoplanet. I'm not entirely sure. Then we have, once commissioning was done, we have the early release observations, which were programmed by SDSCI astronomers, and they were designed to showcase JWST's capabilities and to enable scientific analysis immediately. And these comprised targeting fields that contain the lensing cluster and a parallel blank field, a compact group of nearby galaxies, a star-forming region, which is the Carina Nebula, a planetary nebula, and the transiting exoplanet. We also have the early release science observations, which is something that was a competitive process where people applied for time for projects which would show the capabilities of the instrument of James Webb using multiple instruments simultaneously. And these are being taken at the same time as the cycle and approved programs. However, they have to be completed within 6 months of commissioning ending. So most of these observations will be done by early next year in theory. So new results from James Webb Space Telescope. As of yesterday, there were over 100 papers and telegrams submitted for publication using JWST data. And these involve things from commissioning results, description of science instruments, citizen science astronomy of people who are following the deployments of JWST until it got to L2. And these also involve supernova discoveries, detection of exoplanets and planet atmospheres, protostars, you name it, extragalactic globular clusters, gravitational lens galaxies, stars, and a lot of stuff in extragalactic astrophysics. So this is more of a laundry list, which I don't want to go through all of. And there are many papers, and these increase daily. So any summary that I'm going to do about this will be terribly incomplete, and of course biased by my interest. But here we dive into it. So exoplanets. While James Webb was not actually designed for discovering exoplanets, it uses the exoplanets that were discovered through the careful monitoring made by satellites like Kepler or TESS, or even from the ground. But these observations really aim at characterizing the known exoplanets using by measuring their physical properties such as mass, size, surface temperature, and particularly the chemical composition. And these new observations will show how these other planetary systems compare to our own solar system. So one result that came out recently is WASP 39b, where it is the first detection of carbon dioxide in an exoplanet atmosphere. So this is a fairly hot, around 1200 Kelvin, transiting exoplanet that orbits a G7 star, which is close to solar, in a period of little over 4 days. So the mass that is measured is about 30% of Jupiter, and it's got a radius which is about 1.3 times the radius of Jupiter. While the presence of carbon dioxide was hinted by the Spitzer observations, James Webb detects this line at a very good signal to noise. And on the right, we actually see the spectrum and the analysis and several different analyses that were used to reconstruct the spectrum from either from the imaging. No, this is from the GRISM spectroscopy. And in the bottom, we have the filters of two of the filters in the Spitzer telescope. When this allows you improving some of the models for the atmosphere of this exoplanet. And these best fit models have a metal enrichment, which is about 10 times larger than of the sun. And yet it has a subsolar carbon to oxygen ratio of about 0.35, whereas solar is 0.55. So this tells us that even within this population of exoplanets, there is a big diversity compared to the solar system. And all of these will tell you whether you would find the conditions that enable formation of life or not. Another example, this is of high resolution imaging. And this is of an exoplanet with its telephone number there. And we actually see in the left, we see the position of the star, which is completely occulted by the coronagraph. And the bright spot that we're seeing there is actually this exoplanet, which is, I think, it is comparable to a brown dwarf in terms of mass. And this was observed going from NIRcam wavelengths, which is start at about 2.5 microns out to 15.5 with MIRI. And on the right, we have a modeled spectrum which combines data coming from ground-based observatories plus the James Webb data, which are on the extreme right. So all of these data points here, they come from the observations with James Webb. And this allows you to have a very good constraint on the model of this source. From there, we infer a mass of about 7 times the mass of Jupiter, a temperature of about 1300 Kelvin, and the radius of about 1.5 times the radius of Jupiter. One of the things that James Webb has been used is to observe single stars at large distances, and this takes advantage of strong gravitational lensing, which is caused by clusters of galaxies. So this requires very favorable conditions. You need a star that falls on the critical curve of the gravitational lens. where its signal can be amplified up to thousands of times. And since the stars move due to their internal motions in galaxies, these observations are considered as transient phenomena, though the time scale for us on Earth may be long. The use of gravitational lensing to explore objects in the universe has been used previously by the Ogle survey, which would measure microlensing events in the towards the Milky Way and the Magellanic Clouds to detect exoplanets. And there are quite a few exoplanets that were detected through this effect. So this is a picture of this magnified star at 6.2, which is called Earendel, which stands for the god of the morning star, according to what Wikipedia tells me. I know this name from Tolkien, so it's not completely far-fetched. And what we see, it stands on the lensed galaxy, and this is completely distorted. So this star has some challenges in its reduction because you have to remove the contribution from the galaxy when you're trying to measure its brightness. But we see the models, and they're completely compatible with a point source. So in the bottom right, we see absolutely no evidence of residual light. By fitting these measurements, it's possible to derive some stellar models that describe it. So on the left, we have a model which considers a single star, and this has an effective temperature of about 1500 Kelvin, which makes it a really hot star and pretty massive. Or it can also be fit with a comparable signal noise as if it were a pair of stars, one with an effective temperature of about 10,000 Kelvin, which is comparable to an A star, probably something like Sirius or Vega, and another one at about 30,000 Kelvin, which would be an OB star. But to have a better handle on this, we have to await until spectroscopic data are taken later this year. Another thing that James Webb has been able to show in the ERO data is the presence of extragalactic globular clusters. So globular clusters are self-gravitating association of stars that can contain up to 10 million stars, and they have symmetrical shapes. And at least for the Milky Way, they tend to be found in the galaxy's halos. And these also tend to contain the oldest stars that we know of. But globular clusters have been detected in several nearby galaxies. In the image of the lensing cluster SMACS 0723, we see a large number of concentrated sources whose properties are consistent with globular clusters, which are located in the intracluster medium, or that means they're located in the space between the different galaxies that belong to this cluster. But there are also some globular clusters that are associated with a multiply lensed background galaxy. And this will give us some insight on the properties of globular clusters when the universe was about half its present age. So this shows an image of the SMACS 0723 cluster, and we highlight in the center the brightest galaxy, and between this galaxy and a neighbor, there is a hint of some of these sources. But for you to make this measurement, again, you have to subtract out the background. And this is done by filtering the light. And once you filter that out and subtract it, you actually have the measurement of these objects. By looking at the profile, in other words, you count the number of these globular clusters relative to the center of your brightest galaxy, you can actually find the distribution. And this is compared with the dark matter profile, which is derived from the lensing measurements. And both of these are probing the dark matter that is present in this galaxy, and these seem to show a very good agreement. And these are the colored lines, whereas the green line is fitting a given profile, which is normally used for galaxy work. Now, these are the globular clusters found associated to this background lensing galaxy at about a redshift of 1.4. And each of these were measured, each of these objects had its flux measured in different filters. And from there, the authors try to recompose their star formation history. And for many of these, those put in red, we find that the peak of star formation that created most of the stars in these systems was at about ranging from redshifts of 11 to about 9 to 8 in terms of redshift. So this is really early in the history of the universe. There are some which had their peak of star formation more recent. So these are not all systems that were formed at the same time, which is what we see in the Milky Way. Once we go to field galaxies, not those in clusters, one of the main findings of the JWST has been the number of disk galaxies at redshifts greater than 2. There are several reasons for this, and most of them are selection effects caused by our previous observations. One of them is the cutoff in atmospheric transparency by for ground-based observations. You also have the seeing, which is turbulence in the atmosphere that affects the resolution. You also have, for some of the space-based observations, the relatively short wavelength cutoff of the Hubble Space Telescope. And for the other satellite that would observe galaxies in the infrared was the low resolution because it was an 85 centimeter diameter telescope. And a fair number of papers that came out analyzing the JWST data within the last 2 months focus on the morphological properties of galaxies at these redshifts. So we have an idea. Here I show some very early observations taken with HST using Wide Field Camera 2. We have images ranging from the ultraviolet to the near infrared. So when you're looking at high redshifts at a redshift of 2, what you're seeing with Hubble in the in Hubble's near infrared bands is something like this, which is dominated by some of the knots of star formation and maybe the nucleus of the galaxy. On the upper right, we have Spitzer data, and we see that, well, we can see that these are extended sources, they're not stars, but you can't say much more than that they're extended. Whereas the same objects in JWST are shown below, and we see this incredible increase in resolution. Doing a objective analysis of several of the ERO fields that had data available, this group from Nottingham and Manchester, they actually calculated morphologies for galaxies with estimated redshifts between 1 and 5. And the plot in the bottom shows the morphologies that were identified using HST only. So we see that there's a preponderance of spheroids relative to disks. But once we go to JWST, this thing completely changes. So we just didn't have the information necessary to make a good classification of these galaxies. And we see that as far as Percuda galaxies are concerned, there's not really much difference. And a different analysis, this using artificial intelligence applied to one of the public surveys, finds that the distribution of these objects is very consistent with what we call a Sirsic parameter, which is a way that you mathematically describe the profile of disk galaxies. And disk galaxies have this coefficient of this exponent of about 1, and the majority of these galaxies are completely consistent with this. So here we have 2 different methods which are completely numerical, that saying almost the same thing, that these are real disk galaxies and they do not depend on individuals classifying them. Oops, sorry. Another interesting feature here are these dusty disk galaxies that were undetected by HST. So here we have one image from HST and another one from James Webb of exactly the same field. And this galaxy is not there. So these are found by looking at color plots where you're comparing flux ratios in different parts of the spectrum. We see that they actually form a niche of their own. And these are galaxies which have a large amount of dust in them. They are not necessarily small, which is measured by this parameter here, which is called the effective radius. And some of them are pretty bright. And most of this because they probably have a lot of star formation going on, which is absorbed by dust and then is re-emitted in the infrared. As we go further on, we try to reach out to the redshift frontier. And because of the cutoff of HST at about 1.8 microns, it is very hard to use HST to unambiguously detect galaxies of redshift greater than 11, because you need to have at least 2 bands to say that your detection is real or not. Obtaining redshifts from the ground using spectroscopy for these galaxies is very tricky business, because you're limited severely by OH emission in the night sky and by atmospheric absorption. And most of the emphasis on the early science papers on JWST has been, not surprising, on galaxies at redshifts greater than 5. But because the telescope is not fully calibrated, there is a paucity of, and there's a lack of spectroscopic redshifts to calibrate photoses, there can be differences. So a lot of these measurements that have been done so far should be considered tentative. One of the first surprising results, which was made by one of our grad students here, is obtaining a redshift 6 spectrum on data that were used to calibrate the telescope. This has very strong emission lines. It is a fairly high redshift. And what we see from, we take spectra in 2 different orientations, is that this is probably caused by bursts of star formation, which is due to a merger. This is the parallel field to the SMACS 0713 cluster, and this image is not so well known. But with this group in Manchester and Nottingham, they actually identified several high redshift candidates. And there has been a lot of discussion in the literature whether these numbers, this high number of high redshift galaxies, is compatible with models or not. But it is quite likely that there's a fair amount of contamination. So this group actually compared the number of detected objects that they have with several models. Even though it is high for most of the models, it is not necessarily higher than all of them. So it is hard to say whether these numbers of galaxies are incompatible or not with what the models predict. One of the best candidates for high redshift galaxies, this one that was discovered by a group led by people in the University of Texas, where it is fairly isolated, and you use the dropout technique where basically you see no flux in some of the bluer filters, and then you start seeing it in the redder ones. And this tells you where the position of the so-called Lyman break is. And this gives you a very strong signal on what the redshift could be. And using photometric techniques, we have this estimate at about a redshift of 12. And on the right, we see what the observed color of this object is. In the left panel is the observed, which is red. But when you go to the rest frame, this is very blue, suggesting that there's a lot of hot stars in this object. Now, what are we doing here at the U of A? We have 2 instruments that were built by people here. One which is NIRcam, which was PI'd by Marcia Ricci, and there's MIRI, which is a mid-infrared instrument, which is co-PI'd by George Ricci. And a lot of the hardware was actually built here in the university. We have been actively involved in instrument testing prior to launch and then after commissioning. And a lot of us are involved in large surveys of exoplanets, characterizing debris disks around stars, measuring galaxies with nucleativity. My work in particular is in this item where we teamed up with the NIRspec team in a very ambitious survey to observe spectroscopically and photometric using over 800 hours of JWST time in 2 specific regions of the sky, with observations starting early next month. And this shows on the sky 2 of these regions, which are called Goods South and Goods North. And just this gives you an idea of what the coverage is going to be, both with the photometry, which are all the squares in orange and pink, and spectroscopy, which are the green and blue squares. And the same goes for Goods North, and these are opposite parts of the sky. So to conclude, what we can say is that JWST is performing better than the requirements. And thanks to optimal launch, the expected lifetime of the observatory is estimated to be at least 20 years. Some of the limiting factors might be the micrometeor impacts on the mirror and maybe failure of the mechanical components. But we're doing the best we can to use the mechanical components as easy as we can. The scientific analysis submitted for publication already have had a big impact on our understanding of galaxy formation and evolution, the properties of exoplanets. And of course, as with the HST, we should expect results that were unforeseen at the time of launch. With that, I thank you for your attention.
Great. Thank you so much, Dr. Wilmer. I think we have several questions that we'll address, and I just will also let our members know that Dr. Wilmer will stay around and will be here for our members only section of the meeting later. So we will answer the questions that you have now, but our members will have another opportunity to interact with Dr. Wilmer later too. So do we have some questions from Zoom? Okay.
All right, questions from Zoom. Mike Wiesner asked, tracking moving sources, what types of objects, how fast?
I think it's up to about, I think we tried even faster than the requirements. I think it's around 67 arc seconds per minute. I don't recall. But the type of source will be mainly asteroids and comets. And
Okay,
that's
yeah.
why we have this picture of Jupiter. All the planetary guys, the solar system guys are really interested in this.
Yeah, okay. Richard Spitzer asks, why the diffraction lines coming from the stars?
Well, this is because of this is caused by the mirror array. So even though we don't have, let's say, a secondary as you have on a Newtonian telescope, the whole mirror creates a diffraction pattern. And this is true not only on the James Webb, but it is also true on Keck, which has the same kind of segmented image. You have multiple segmented images. And it is also going to be true for the GMT and the other large telescopes that are going to be put in Chile or Hawaii.
Okay, Savan asks, can weak lens correct for support and hexagonal mirror diffraction spike losses, or is it for relative photometry only? Does that make sense?
No, could you repeat, please?
Can weak lens correct for support
No.
and hexagonal
No,
mirror diffraction?
No, it
No,
cannot.
okay.
No, the weak lens, what it will do, it will defocus. So it will act, well, the purpose of the weak lens is for you to not have saturation, because that will bias your measurements, let's say on a later measurement, and you will not have the photometry at the level. Because we're talking about measurements and the part of the order of 100 parts per million. So saturation is bad news, and that's why the weak lens is used for that.
All right, Kevin Bays, how often will the spacecraft need to use its thrusters? Is this the main limit on how long the telescope can be effectively used?
Well, the prediction is about 20 years. I was looking yesterday at some of it was on one of the weekly reports. They actually used their thruster for the first time about a few weeks back. So this is after we've been in orbit since about February.
All right, and the last one is from Saban. Again, what is the fuel source and can it be robotically replenished?
The fuel, it came fueled from Earth. I don't know if it's possible to be refueled. I think they did leave that possibility open, but I don't really know. But the main issue on a long time scale is the impact of micrometeoroids. And the impact that we had on C3 was very visible because from one moment to the other, the quality of the images was really bad. You can correct it, but it has a big effect. So every time you have an impact, there's a slight degradation in the image quality. And the other limiting factor, you have these micrometeoroids beating on the mirror, but you also have them hitting the sun shield. And once the sun shield is torn, there's nothing you can do. Oh, okay.
And do we have questions from social media? Yes.
Our social media questions. First one is how far back can you see in space? I
Well,
think
the furthest back you can see in space is the cosmic microwave background, which is a redshift of 1,000. After that, you have the dark ages, and this is where a lot of the research is going. So some of the papers here that came out recently, they want to say, oh, we've measured galaxies at a redshift of 20. And that's how far we're going to push. But there are limitations as to how far you can go, at least with James Webb. And also whether you will be able to see it because of the transparency of the universe and so forth.
all right. How often does a meteorite go by? I think they're talking about impacting.
Yeah, there are models for this. There's actually a paper on models for this. The one that impacted C3 was considered to be an event that would happen once every so many years, but it happened right at the beginning. But there are models that predict this, and there actually was a discussion. I don't recall if it was on Space Telescope. I think Space Telescope had a discussion on this, whether these are meteors that come from on the path of a comet, or if these are just some random meteor because, you know, of all the perturbations that these have by the planets.
All right. Getting more questions here. If the calibration of the instruments is based on current theories, how are the expected versus observed data informed us about the deficiencies of the theories?
Well, as an observer, the greatest pleasure in observer is to prove that the theory is wrong. So, but to be on a more serious tone, we actually work in tandem with the theorists, because a lot of the stuff that we do with James Webb is actually based on theory to guide us on what are the type of tests, what are the observational tests that you have to carry out to make the analysis. So nowadays there's a lot of cross-fertilization between people who work in theory and who work in observations.
Okay. Is there a time before time? This was something somebody heard Michael Keiko talking about.
Well, when you talk about physics, you cannot talk about anything before the Big Bang. And I think a good source to explain this are Stephen Hawking's books.
Okay.
It is not physics anymore.
Right. Okay. Is it believed that most stars have exoplanets?
I would think so, yes. But that doesn't mean that you can observe them. I mean, we know that there's a very large proportion of double stars, and there's no reason why not, but you can't say by a priori that you will find an exoplanet.
Okay. Have there been any physics theories proven by the new observations of JWST?
Not new physical theories, but certainly these measurements that we have with gravitational lensing, they're great support for the general theory of relativity.
Okay. I've been keeping track too. We've had people on Facebook from Minnesota, Iowa, North Carolina, Yosemite National Park, Florida, Montana, several from Tucson, North Hampshire, New Hampshire, Southern Philly, California, Ohio, and Michigan. It's been a wonderful audience.
Wow.
Oh, thank you so much for that breakdown. That was really great. About 150. Okay. Okay, so now we're open to questions from people in the room. Remember that I'll have to reach you for you to ask your question through the microphone. So if you raise your hand. Okay.
Yeah, I was wondering how fast the JWST is traveling on its orbit.
Yeah, I don't know the answer to that one.
Okay, someone else. Yes.
Yes, I was wondering, does the telescope do science 24/7 or is there a downtime?
No, it observes 24/7
Oh, okay.
unless there's a problem. And that is one of the differences relative to HST. HST, because it's orbiting the Earth, you have at most an observation window of 40 minutes, unless you're in one of the so-called continuous viewing zones. But James Webb does not do that. So the maximum time that you're limited to is by the amount of data you can store on it. And that is considered to be about 24 hours. So when you look at a planetary transit, that is absolutely critical that you're homing on that object and you don't budge, a milliarc second.
Okay, thank you.
Right. Okay, someone else.
There.
Okay. I'm going to try to do the same area of the room first.
How is the telescope pointed? And can you move from one part of the sky to the other part of the sky easily?
You can. There are several small telescopes that allow you to do the pointing. And actually at the beginning of commissioning, some of these were not well calibrated and we would lose the calibration on occasions mainly because of software issues. And once those were fixed, the pointing started very well. The problem of you going from one part of the sky to another is that it takes quite a bit of time. So and we had this a few times, we were going from the north ecliptic pole to the south ecliptic pole, and this movement took something like 30 minutes or longer. So you have to wait until the telescope moves its orientation.
You need to ask your question through the microphone.
You explained the pointing mechanism that they're pointing telescopes, but not the movement. Are there gyroscopes in there or something that shift to cause the movement? What's the actually movement mechanism?
That I don't know. I'm sorry. I don't think they're gyroscopes because if we're based on the concepts of Hubble, we know that those don't work. I think it's a different mechanism, but I don't know what it is.
Okay, other questions?
There's one here on row number 4.
I'm going to get this one and then I'll head down. Okay.
What is the latency of the data coming back from Webb to the ground?
It depends on whether we have any channels open on the DSN, which is the network. And one of the things that we on James Webb are really eager is to have Artemis launch soon, because it's going to use a lot of bandwidth. Particularly once we start having these large surveys coming in, it will impact us pretty badly, because you only can store so much data on the telescope itself, and you have to transmit it to Earth.
Questions in this area? Okay. Okay.
How many ground stations do you have
3.
pulling this data down?
We have 3. We have one in California, one in Spain, and one in Australia.
Okay, thanks everyone for being patient. We will get to everybody's questions. So.
You have the instruments that actually have to sense the light. There are 4 main ones, is that right?
Yeah, we have, well, they're all important.
Well, okay, but how do they switch between, they have to be at the prime focus for the mirror,
No, they're
Oh.
all on the prime focus.
okay,
And the same is true for Hubble.
okay,
And the one thing that I did not mention is that when we're doing our survey,
yeah,
we're actually using 2 instruments simultaneously.
okay,
And Hubble does the same. So you can use, let's say, ACS, which is the visible camera, and you can use wide field camera 3.
okay, I understand, I got you now, I just didn't think you'd have some kind of lazy Susan.
No,
Okay.
no,
That
you
makes
you
sense.
can you
Yeah, got
actually have several instruments on the
Okay,
photo.
that makes sense, thank you.
Okay, there was some, yes.
Do you think the scope will ever be used to image true disks of stars? It would have the resolution for, let's say, Betelgeuse and Antares, some of the supergiant stars, and perhaps even Alpha Centauri, although it's much smaller and they're about the size of the sun.
Well, Alpha Centauri is on the list of objects to be observed, if I'm not mistaken. They're looking for planetary companions. But there's nothing, if you have the coronagraph, you can actually do that. And I know there are projects which will be observing the debris disks around stars, because these are very much related to the formation of planets. But it's just a matter of people putting in the proposal, and it seems to me that this would just be natural.
Other questions in the audience here? Okay, great. Well, thank you so much, Dr. Wilmer. And we will look forward to you hanging around, Dr. Wilmer, and talking with our members a little bit later.
Okay.
So,
I'll
Thank-
just turn this thing off
okay, thank you.
and I'll leave
And
Zoom.
next on the agenda, we have Doug Smith, who's our who's our Astronomical League coordinator. And Doug has got some awards to give tonight. We participate in the Astronomical League programs, and in that way, people look for things and find them, and then they get rewards for creating a list of observations that they've done that meet a certain set of criteria. So, and Doug has got several awards. So he's getting his stuff out right here on a table. If there's anything I can do to help Doug, just let me know. Oh, okay. It's being heavy because he's got several awards that are
The data are being stored in the
encased
telescope.
in frames.
Do you want me to?
Okay, if you might want to stay a little over here where the camera can see you,
Oh,
or we can
sorry, I
get you
should
in
turn
the
this off.
camera.
So I have a bunch of awards to give out tonight. The first one I'll give out is to Brad Shaffer. Brad gave a wonderful talk last month on his analemma experience, and he submitted a nice thick paper for his analemma award. I'll return that. And his award, he gets a nice, beautiful framed plaque. He gets a beautiful pin to go with it. And a letter. Okay, so the next bunch of awards I have, I'm going to call the names because we've got 4 names. And these are people who did a lot of outreach activity in the last year. And so these are all Special Astronomical League Outreach Awards. So as I call your name, please come down and don't go anywhere until everybody's down here. And that way you can applaud the whole group for the awards. Ben Eisenstein. Tim Lawler. By the way, Tim is getting 2. Only 1 pin. Barbara Whitehead. Barbara is also getting 2. Robert Rose. This year's outreach group. We've got 3 more people, but they weren't present tonight, and they'll get their awards later.
Thank you so much, Doug. We're always happy when people get the awards, and these are such fun programs to do. So if we have people out there who haven't tried one of them, you might want to look up Astronomical League and look to see what fun kinds of activities that you can do. And also that then you can apply for the award for it. So, okay, our next item on the agenda is Jim Knoll is going to share some information about events.
Okay, I'm just going to show a quick screen here on some of our upcoming events. And for anybody that's still on our social media, if you're in the Tucson area, you can certainly come and participate with these. This month, we have one tomorrow night at Canoa Ranch. Unfortunately, it is filled. They capped it at 75, but there are future ones for that. So just check our calendar. If you go to the TAAA website, you can check the calendar to see when they are, and then you go to Eventbrite to register. We have 2 at Oracle State Park, and in just a minute, we're going to have a couple guys talk about those. They're on the 23rd and the 24th of September. And then we have one down in Sunsites, actually, in Cochise County, also on the 24th at the community center. And then a few of them in October. We've got Agua Caliente Park on the 1st, Catalina State Park on the 15th, Chiricahua National Monument on the 22nd. And then twice a year, we open up our Chiricahua Astronomy Complex to the public and to the locals here in Tucson and around Cochise County. And we call that Evening Under the Stars. And so there's a process on the calendar, or you can go to the Facebook event, and there's a process there for you to be able to register and let us know about those. So those are some of the upcoming events. So what I want to do now, either Mike or David, I'm not sure who wants to speak first. You should be able to unmute yourself now, but go ahead and say a couple minutes worth on the Oracle State Park.
So I'm going to speak first. I'm Mike Wiesner. I live up in Oracle, and I'm going to talk very briefly about the David H. Levy Arizona Dark Sky Star Party that's going to be held here at Oracle State Park, September 21st through the 25th. For those of you who don't know, In 2014, Oracle State Park became the first park in the Arizona State Park system to be designated an IDA International Dark Sky Park. Early on in the planning for our event this month, the community of Oracle became very excited about the event and is doing an Oracle Dark Sky Cultural Festival in conjunction with the event. There's going to be star parties, music, art, food that are open to the general public. Explore Scientific is the organizing company for the event. Several of us here in Oracle are on the organizing committee. To learn more about the event and to see registration details, go to explorescientific.com/ADSSP or explorescientific.com/Oracle. Either one of those links will work, and registration slots are still available. When you're on that webpage, click the large red text on the page that says schedule updated to see the updated schedule as of today on what's happening, where it's going to be, and when. Registered attendees will get special access to the park, including all night long. They're going to receive gifts from Explore Scientific, have in-person access to the amazing guest speakers, and be eligible for some incredible door prizes that will be given out on Sunday morning at the closing session. Again, the dates are Wednesday, the 21st of September to Sunday morning, 25th of September. We look forward to seeing many of you in just 3 weeks. I'd now like to introduce the most special guest and featured speaker at the Arizona Dark Sky Star Party. To give him a proper introduction would take me several weeks, but since I only have a few seconds, I'll just say that it is an honor to introduce the friend and mentor to astronomers all over the world and Dark Skies Arizona resident, David Levy.
Well, thank you very much, Mike. And I really appreciate the chance to say a few words about the forthcoming Star Party at Oracle. I do want to say first that I really enjoyed tonight's talk on the James Webb, so much that I agree with my Canadian friend's decision to rename the telescope. It is now called the Just Wonderful Space Telescope. I like that idea. One of the things that the James Webb is not going to be able to do is to join us at the Oracle Star Party. But this telescope, which is right next to me right now, Minerva, will be there along with all of your telescopes. The main purpose of being out under a dark sky for 4 or 5 nights is to remind ourselves why we became interested in the night sky in the first place. And it is to not so much to see the sky as well as the James Webb would see it, but to see it as well as a poet would see it. For example, William Blake, who wrote, "To see the world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour." Thank you very much.
Thanks, guys. I'll turn it back over to May and we'll continue on.
Okay, thank you very much. Eric Kurkashka, Dr. Kurkashka is not here tonight, and our members are used to him giving a planet report each month. He is out of town currently, but if you look on the website where his blog is on at TucsonAstronomy.org on our website, you will be able to see that the last planet report he did includes this month. And so you should be able to find planet information for September on the website. And he is planning on being back next month. Okay, I want to, at this point, thank everyone who has participated, and I would like to thank our people on social media for coming and joining us. We are here every first Friday of the month, and we're delighted to have you join us. Our webpage is always there, and we hope that you will look at a lot of the wonderful astronomical information items that we have on the website, and that you will, keep track of our events and visit us often through social media. The contacts that you have, and let us know if at any point that we can be of any help. And you can also, of course, join us, join our club through the website as well. So thank you so much, social media, for being with us tonight. We'll say goodbye to you for this evening, and we hope to see you next month.